thinking about. All right. So, again, mastery test Wednesday and later. But easy parts in here, you're going to do ones like this, not all of them, more on during your recitation. So we're going to do some easy questions that you like, and then move onward, just like after we go through this today, we're going to move onward. And then in your next recitation, you're going to do some medium to difficult level, the ones that were passed out to you or distributed online to you on Friday. Those are like the difficult variety. So medium would be maybe just product rule, just chain rule, not a whole bunch of levels of those. So in between. Something like this, though, what we talked about on Friday. When you see a horrifying looking expression, if you're supposed to, for theoretical purposes, prove that you know how to take the derivative of that, look at the overall structure of this, or think about if I were substituting in numbers for x, what would be the last step order of operations that would happen here? So what's a general overall rule of the main g of x function that's going to happen? Yes? Okay. Yeah, so how are the pieces of g of x connected overall, like the last outermost connection? Yeah, product rule. So we've got a product, two fractions that are multiplied, and so we know how product rule works. Like we talked about on Friday, if you want to make yourself up some symbols to kind of help organize your thoughts, here's one piece, here's the other piece. Maybe call this, what letters are not in there? A of x and b of x or something like that. So product rule says I need a prime times b plus b prime times a. Whatever order of multiplications within those products is fine. Whatever order of addition between the two halves is fine. But how would I find, for instance, the derivative of a, that first fraction there? What overall rule is going to help me find the derivative of a of x, or whatever you want to call that first fraction? It's a quotient, right? So we're going to use quotient rule. All right. So I'm not going to make further names for pieces, but to find the derivative of a of x, we need quotient rule. And let's see, quotient rule involves a quotient, the denominator of which is the original denominator squared, right? So log base 5 of sine of x, whole thing squared. All right, now, as for our numerator, it's going to be a mess. But in the first half of the numerator, which of these two expressions derivatives do I see in the first half before the subtraction, the numerator? The cosine or the log? Whose derivative shows up first in the subtraction? Yeah, derivative of the numerator times the original denominator. So I need to find the derivative of this expression. Let me just jot this down here. If I want to find the derivative of cosine of natural log of x, I've got a cosine function and a log function, so we get to use chain rule. So whatever order you want to think about this, inside out or outside in, we need to find the derivative of both a cosine function and of a logarithmic function, natural log. So what's the derivative of cosine of x? Negative sine of x. So this time we've got cosine of natural log of x, so we should have negative sine of, same thing, natural log of x. That is, leave the inner function intact, and as a separate factor, multiply on the derivative of that. So natural log of x, derivative is 1 over x. Yay, at least finally one simple derivative here. So 1 over x. So this is cosine of natural log of x's derivative. Let's see, let me change colors here. We're looking at the denominator of this first fraction. Log base 5 of sine of x. We need to find its derivative. So chain rule again. This time the outer function is the logarithm and the inner function is the trig function. So let's see, log base 5 of x, its derivative would be 1 over a product, right? 1 over x times the natural log of 5. This is going to be 1 over something else times the natural log of 5, right? Sine of x times the natural log of 5. That's the logarithm function's derivative with respect to the sine function. And the derivative of sine of x? Yep, cosine. So sine of x, cosine of x is its derivative. And you put this on the top if you wanted to. Any of these could be condensed, but don't spend your time on your mastery exam putting things together and simplifying. You could just write them straight out. Now, I have a limited amount of space and need to write really big, so I'm going to kind of do this in a slightly different way than I hope you can piece together on your mastery. But for our second fraction, well, let's see, this a of x, we have all the pieces we need for our numerator, but I've got this is going to be in the first part. I need that numerator, cosine's derivative, this expression, times the original denominator. So 1 times 2 minus, let's see, the other pieces that we have. We need the derivative of the denominator, 3, call it this expression here, and the original numerator, 4. So I'm just abbreviating what this a prime of x is. We need the derivative of our second fraction also, which is again quotient rule, maybe slightly less messy than last time, but just as many chain rule pieces needed. So if I want to work on the derivative here, let me change this to some different colors. Let's see. Numerator, 6 to the negative 8x power. What sort of function is this? Is this a power function or exponential function? Exponential, whisper, whisper. Yeah, exponential. Remember, exponential functions are numbers with variable powers, and they show up in their own derivative. If I have 6 to a something or another in my original function, when I take its derivative, I'm still going to have 6 to that exact same power in the derivative with some extra pieces. If you're using power rule, that's for power functions, x's, or some sort of variable expression raised to a numerical power. That's when you decrease the power by 1. So this exponent isn't going to get lower by 1. If I'm dealing with 6 to the negative 8x and finding its derivative, let's see, e to the x is the easy one. E to the x is its own derivative. If it was just 6 to the x, I'd have 6 to the x times natural log of 6. This is 6 to the negative 8x times natural log of 6. And what else do I need? Times negative 8. And feel free, you can just write it like that. You don't have to be fancy and try to write them in the front like coefficients or anything. Just make sure you do use a multiplication symbol, especially here, so it doesn't look like you're subtracting 8. All right, so that's the derivative of the numerator. And then the derivative of the denominator. Let's see, what do I have? Black. Square root of x plus e cubed, whole thing to the second power, whole thing squared. So that denominator, something with variables raised to a numerical power. That's power rule that we get to use to find the derivative. So it's just squared. If it was x squared, derivative is 2x. If it's something else squared, when I take the derivative, I'd have 2 times that something else, all to the first power. You don't have to write first power exponents. And then, let's see, I need the derivative of the base of the exponent, the derivative of square root of x plus e cubed. How many terms does that derivative have? 1, right? E cubed's derivative is 0. Yeah, so you could write plus 0 and make it 2 terms, I guess. But yeah, just the derivative of square root of x needs to be tagged on here. 1 over 2 times the square root of x, as we've gone over multiple times. You could write plus 0 if you want. It would be in parentheses if you do that, but here's the derivative of that inner function, the thing that was squared originally. All right, so setting up the second fractions derivative is going to be kind of similar. So b prime of x would involve these 2 derivatives. This one goes first in the numerator. And then the, box this out here, the original denominator minus the denominator's derivative times the original numerator. So denominator's derivative times the original numerator. So 3 times 4. So not an ideal notation to write these in, but as you can see, there's a lot of stuff here. And this is all over the original denominator, that squared expression, squared again. So just a point to make here. Again, you don't have to do any algebra simplification, but you can either write this as, since it's not a whole bunch, just that expression squared, or since it's a squared expression squared, you could also just write it to the 4th power. It's not a major thing. It's kind of like if you had a 3 times 4 and you wrote 12. I'm not going to say, oh, you shouldn't have simplified. Whatever you like. But in any case, we found the derivative of that first ugly fraction. We found the derivative of the second ugly fraction using quotient rule in both cases. There's one more piece to put these together, and that's just quotient rule. I'm not going to write it out with details, but just, or product rule rather. Just g prime of x. Using the names of the functions as we define them, we need a prime of x times b of x, the original, plus, next line, b prime of x times a of x. And I think I said that first, but we can fill in those gaps with this, but as you can see, writing something like this takes a lot of space. On your longer portion of your mastery test, the one that has hard questions on it, you'll have like, you know, the whole paper wide to do like one question, half a sheet of paper, so that you can write out what you need, show all the steps. Please don't leave your answers with things like 1s and 2s and a prime of x and stuff. Please actually write them in. But as scratch work to help yourself organize, I really suggest doing this when you encounter a long problem. This one might be a little bit more challenging than what you're actually going to see on the mastery test, but if you can work your way through something like this, then you should feel good going into that. So, all right, that's enough mastery stuff for today. I'm going to see you again do some more of this next time. But the reason we're dealing with all of this is because derivatives are useful. So, there we go. Derivatives are useful. The rest of the semester, we're going to be working on how to interpret expressions like this using derivatives, solve some problems using them, and even just graphical representations of functions, figuring out what we know about, if I see a rate of change graph, what I know about the accumulation, or what I know about the rate of change of a rate of change graph. That we haven't talked about just yet. Or if I have a graph of an accumulation function, a graph of how much of something I have, what I can tell about the rate of change by looking at it on what intervals, being more specific than maybe we were in the past, and then, again, how that rate of change varies through the domain of the function. So, in any case, volume of concrete in cubic meters poured during a construction of a skyscraper. Suppose it's given by this. So this is a volume function, not velocity or something. Volume in cubic meters is given by this function rule, v of x equals 30 times 1 minus e to the negative x over 15. Much less unusual function than the thing we just saw. Much more realistic for applications, are not such strange functions. But when you do encounter something that's simpler, don't just give up on all your derivative rules. That's why we need them. So x in this case is measuring the elapsed time in seconds since we started pouring the concrete. So first question, this function is telling me how much concrete I have in cubic meters at any point in time in seconds past when we began, at time x equals 0. So first of all, take a minute, see if you can figure out the closed form function to give the rate of change of the pouring of the concrete, meaning the rate at which it's being poured in cubic meters per second. Since our independent variable is in seconds, a rate of change of this without doing fancy conversions would be in cubic meters per second. A function for volume, we want the rate of change of that volume. All right, so what operation, what mathematical magic did you just do to get this? What did you have to do to answer question A? Just in general. Find the derivative. Yay. Yeah, so we need to find the derivative. Derivative of something like this. Doesn't look too bad. All right, closed form function that gives the concrete pour rate in cubic meters per second. Let's see, what is this 30 here? It's a constant coefficient or a constant factor. So I don't need to use product rule with this, although if you do, your answer will still be correct, just extra steps. But if I want to find the closed form rate of change, I can call it v prime of x or dv of x dx or whatever notation you'd like. But we want an exact closed form. So constant factor 30 carries through. And then we can simplify it later if we want. This one is fairly short, so it'll maybe be easier to simplify. But the derivative of the rest of it aside from that factor of 30. By the way, you could distribute the 30 if you wanted to. But a constant factor of 30 on this two-term expression, what's the derivative of 1? 0. If you had distributed and had it as a 30, derivative is still 0. All right, and then minus sum and difference rule. 0 minus would just be negative. What about the derivative of e to the negative x over 15 power? E to the negative x over 15, right? Exponential functions show up in their own derivatives. But we do need chain rule. What's the derivative of that inner function, in this case, the exponent? Negative 1/15th, right, thank you. So negative 1/15th. All right, so here's a kind of ugly version of this. But in the parentheses, you can see there's a negative multiplied by another negative. So there's not going to be a negative coefficient. I'm just going to have a 30 and a positive 1/15th. If I want to clean this up a little bit, 30 times 1/15th is 2. So I could call this 2e to the negative x over 15, just to be able to write it more succinctly, because we're going to do some other things with this. For instance, going back in time to things we did earlier, but just starting from a different point. At 10 seconds past the start of the pour, so we started pouring concrete. 10 seconds in, there's a light that goes off, and we want to measure just how much concrete was poured since that point in time that the light went off. So onward to indeterminate time in the future. So think about an open form function for L of x, the volume of concrete that was poured after the light went on. The light went on at 10 seconds. So we did questions like this on your second test. What was that, 3 weeks ago? 4 weeks ago? But not starting from the same point we did here. So we hadn't learned about derivatives yet. Remember the toy car question on the test? Something like, how far did the toy car travel between times 7 and 14? Something like that. How can I write an expression for how much concrete is poured after time 10? This L of x function. Ooh. And then we'll do another question, which you can see there. So L of x, it says open form. So that's meaning I'm not going to get a nice succinct polynomial or exponential function or something like that. It's going to be a little bit of a mess, although we have the ability to write it both ways now. How could I use that rate function, v prime of x, to express what happens after 10 seconds? Yeah, integral. So an integral with what limits of integration are we going to have? 10 to x, right. Starting at 10, going through some point in time x beyond that, or actually it would work before that as well. And then what do I write in the integrand? Yeah, v prime of x. Well, I don't want v prime of x quite. I want, yeah, some other variable that we let vary between 10 and x. And what else do I need? dt. Right, so that what I have is then a sum of infinitely many tiny mdx's, rates times an amount of change, or rates times an amount of change in time, so that I get an amount of change in concrete by the time I've multiplied together any of these. So this product gives me amount of little tiny amounts of concrete that we start building at 10 and go through mystery time x. Oops, and I wrote dx, I apologize. This is dt. All right, so L of x, the amount of concrete that has been poured since time 10, or starting at time 10 and going through mystery time x, can be expressed by this L of x function in open form. So how is L of x related to the original V of x? Are they exactly the same? Well, I don't think so. There's this whole thing about a light and 10 seconds and something or another. So L of x is the amount of concrete that was poured since the light went on. V of x is the total amount of concrete that was poured since we started. X is the amount of time elapsed, so that'd be since x equals 0. So what's the difference between L of x and V of x? Yeah, what was that? Yeah, well, in terms of descriptions, yeah, we've got a net accumulation, we've got a total accumulation. This is net accumulation since time 10. If I wanted to relate it to the total accumulation, the total amount of concrete that we have, I would have to add on some extra concrete, right? And the amount of concrete specifically that was poured during the first 10 seconds, what's a function notation expression for the amount of concrete that was poured during the first 10 seconds? Function notation expression, V of 10, right. So the difference between V of x and L of x is 10 seconds worth of concrete, right? V of x is bigger. V of x is V of 10 larger. However much concrete poured in the first 10 seconds plus what happened after 10 seconds, from 10 seconds onward. So for any value of x, or just in general as a function, I'm just going to write v prime of t here, but we could write the actual 2e to the negative x over 15 in this spot as well. But, right, so we've got, if I want to know the total amount of concrete, I have an actual closed form function here. But notice we created an open form function for the exact same thing. We also created an open form function for a relative, for a net accumulation within the domain of this v of x original function we were given. So we kind of went backwards and forwards in the same question. So we had a function for total volume. We took its derivative to find its rate of change. And we can use a rate of change to go back to the original volume, whether part of it or all of it. Yes?
Is the only thing that would make C closed form, like besides x, you have a number?
So if I wanted to express it in closed form, well, it's v of x is this. So v of 10, we could actually calculate that as a number or write it as an expression with e raised to a power, be what? Let's see, 30 times 1 minus e to the negative 2/3. So I could write that expression in here. Now, open form generally involves, it can mean a variety of different things, but something like this where there's actually infinitely many computations implied by this, so a sum of infinitely many, infinitesimally small amounts of accumulated concrete, that's our open form. But it expresses what we mean. So I can express the total amount, y final, by taking some initial value of y, any value that I want, plus a sum of a whole bunch of, since we are at different rates, mdx's. So just kind of general how this relates to our whole constant rate of change from the whole semester. But the idea of this is, before test 2, we talked about this, just start from the rate and write an open form accumulation. But now we also have the ability to, if I have an accumulation function, I can find that rate myself, because, and you can find it yourself, because we know how to find all these derivatives. And so we can re-express things from open form to closed form to closed form to open form. Now, if I asked you to express, if you hadn't seen this original function here, and I asked you, well, if you have v prime of x equals this 2e to the negative x over 15, that's a rate of change. What would the original accumulation function look like? In closed form. It's a little trickier, but if you're familiar with derivative types, you can at least have a starting guess as to how that works, like what pieces would need to be in there. So, let's see. Oh, I was going to say, I don't think I quite answered all the questions here. So I think I said this, but this last question actually just used function notation to relate these. And this does use function notation, but just as a last sort of, before I clear this off, v of x is also just v of 10 larger than L of x. So if it, more succinctly written here, but L of x was this whole integral. Those two express the same thing, but the relationship between them is just that the v of x, that's the total volume from time 0, starting of when we began pouring concrete onward, and the other is starting at time 10. All right, so here's exactly what I was talking about. If you remember, this is actually stuff we worked on during chapter 2, a rocket-powered basketball launching into the sky. And after we looked at it for a while in some numbers, we said, well, here's actually the formula for its velocity. V of t equals t to the 1.3 power. This is a velocity, or a rate of change of its height with respect to time. The height was measured in meters, and time, t, is seconds since launch, so elapsed time after launch. And the 6 meters I just made up for this. I don't think that was part of the original formulation of this. But if this, and this is something we might have done earlier in the year, I don't think it was quite this exact question, but if this is the velocity of that basketball, and I want to express the height at t seconds after launch, that's going to be a total accumulation, but also, well, net if you start at the right point. Take a minute, see if you can express the height, and we'll call the height h of t, at t seconds after launch, just in open form. And there's a second question if this one's easy for you. Yeah, so general question was just asked, so how would I know looking at this that it's asking me for accumulation? So if you notice this v of t is a rate of change of height. So we've got units that were in meters per second, and then we've got a function that we want to know about meters. So if you're going backwards from a rate to a no longer a rate, or from a more complex rate to a less complex, like meters per second to just meters per second, if you're taking away that time unit or one of the per units in this, you're going to have something that's, oh, an accumulation due to, or a net change due to that rate. The rate causes things to change, so how much did we change or vary by? So what about part A? An open form function for height at t seconds after launch. What are we looking at here? Let's see. What sort of operation do I need to put together here? An integral. All right, an integral from, let's see, what's the independent variable of height going to be? T, time. So what's the starting time? 0, right. H of t, we want to measure the height at t seconds after launch. So we're meaning t equals 0 is the beginning of this. So h of t would be, well, 0 through something. If it's supposed to be h of t, I need 0 through t. We have accumulations due to our rate, v here. Now, there's too many t's going on. This time we need to change to something that isn't t, because t was built into the problem. We wanted the independent variable to be t. But I could write v of something or something to the 1.3, whatever letter I pick. I'll pick w. So w to the 1.3 power. And am I done? No, dw, right. We need a mdx sort of expression. And I said x when I was saying that, so dw. So we need our rate times a bit of change in the independent variable. We let w vary from 0 through t. And then we can pick values for t later. We can express it generally as a function. But since this is just what happens past time 0. So what if t were 0 in this function formulation? If t were 0, I'd have an integral from 0 to 0. No time passes, so I have no accumulation, and thus my height would be 0. It's not supposed to be. What is it supposed to be? So what do I need to do to fix that? Plus 6. So as a second term, plus 6. Lots of times you'll see it written in the front. You can write it in the back as well, as long as it's, not, you don't want it inside the integral, like before the differential product or the differential factor in there. So this gives me my accumulation part of that height. And this gives me my starting value, the starting as in at time 0, where we started measuring the accumulation. So I have y initial plus a whole bunch of mdx's. So my starting y value plus a whole bunch of changes in that, dy's, to get my new y final. So open form function for h of t, giving its height at t seconds after launch. So this 6, just as a note, notice this is a height in meters. There are two numbers we had to kind of put in here. This 0 was the time at which the height was 6. So this is a time here in seconds. So just the reason I say that is because I heard a couple whispers of 6 as the starting point for the integral. So when you're looking at putting these together, make sure you're careful about what are my independent and dependent variables. The independent variable in the function is going to show up in the integral, as well as like on the integral sign, as well as in this expression here. We just have to mutate it. We can't have t varying from 0 to t because t is t. So we picked this dummy variable to allow a second variable to fall within our domain 0 to t. But 0 to t are all the inputs to this function then. All right, so let's see the second question here. What do you know about function h of t? Values of it, well, we figured out the value at time 0 was 6. Great. And it increases from there because we had this positive velocity and also because we dealt with this earlier in the semester. But thinking about if I had some sort of mystery function, h of t, and I had h of t's rule written as like some sort of closed form expression, if I then took the derivative of it and it came out to be t to the 1.3 power, what sort of thing could be in this box here that I could take a derivative of and end up with something that looks like this? What type of function would it have to be? Is it a cosine function? Would a derivative of a cosine come out to be t to the 1.3? No. If I'm going to have a variable raised to a numerical power, that's a power function. In order to end up with something like that, what sort of thing would I need here? Or what facts about it do you know? Well, it may be hard to put all the pieces together, but it would have to have a t in it raised to a power. What kind of power would I need on this? 2.3, right. So if you take a derivative of a power function, the exponent decreases by 1. Now, if I take the derivative of this, it's not quite right? If I just said h of t equals t to the 2.3 power. Because if I take the derivative of t to the 2.3 power, I get a coefficient that isn't 1. Notice this has a coefficient of 1. Do you know how you could combat that? How you could counteract that coefficient that appears? By adjusting here. 1 over 2.3. Not pretty, but that'll do it. This is not a standard form for fractions, but that's okay. 2.3 is what? 23/10. So this would be 10/23 in fraction form, normal style. But would you agree that if I took the derivative of this expression here, I'd end up with that? All right, are there other functions that I could have put in the box that would have that exact same derivative or rate of change? Could I change this other than just like making it, whatever, said 10 over 23 instead of this? Yeah, what sorts of things can appear in a function that disappear when you take the derivatives? Constants. All right, well, If I had like a plus 17, its derivative would also be this. If it had a minus 42, its derivative would also be that. But there's one specific number that it's supposed to have, because I know a second fact about function h of t. This 6. I know that h of t's rate of change is given by this, and I know that h of 0 is supposed to be equal to 6. If you were to plug, if I say h of t is lovely 1 over 2.3 times t to the 2.3 power. That's not actually h of t, because if you substitute in t equals 0, you don't get 6. So I can add on any constant I want, and it won't affect the derivative, but it will fix that value, that starting value of accumulation, that 6. So now if I substitute in 0 for t, I can see I get 0 plus 6. At time 0, the height is 6. So we're allowed to change things like that. So this is something that you're going to spend a lot more time on, working backward from a variety of different difficulty levels of rate of change functions or derivatives to finding what causes that rate of change, what accumulation functions have that as a rate of change. You're going to spend a lot more time on that in calculus too. But there are some small pieces of it that we can already see, some easier than others. This is not particularly easy. Power rule, we spend a lot of time on that in class. Power rule going forward, it's like it can look 37,000 different ways. Like maybe it's a fraction with radicals in it. Maybe it's got multiplication where it's really just I could express that as a coefficient and an x or something raised to a power. So working backwards, trying to figure out power rule backwards is a little bit challenging. But we can imagine that there must have been that one higher power and kind of adjust from there. Take an educated guess based on your knowledge of derivatives as to what would have to appear in that original accumulation function whose derivative, rate of change, we already knew. All right, so let's do one step slightly more abstract than this. Let's see. So let's say we have a function r sub f of x, the rate of change of function f with respect to x, that gives the, let's see, that has following two facts. F of 4.1 is -7, and the rate of change of function f with respect to x is this cosine function, 14 times cosine of 7x plus 3. All right, so here's our goal. First of all, we want to write an open form function for f of x. That is, recreate the function f of x, whose rate of change is this, first in open form, and then think about the closed form. So I'll give you a little bit of time, discuss with your neighbors. We'll go through this in a few minutes. There's not a story to go with it, but if you want to make up something about a magical basketball or pouring concrete, feel free, if that helps put the pieces together, or thinking about the units as opposed to just the variable names. right, so if I have a rate and I want to express what happens because of that rate, or r sub f of x, and I want to get f of x. Another notation, you know, if I think of this as f prime of x, is this, and I want to get f of x, the original function back. This is how it varies. If I want to recover that original, what do I have to do to this cosine expression? Integrate it, right. So I'm going to integrate or measure the accumulation because of our rate 14 cosine of 7x plus 3. I probably don't want to write x, but I'll write it for the moment, change it in a second. This would tell me, well, if I put some symbols here, what accumulates between the beginning, lower limit of integration, to the end, upper limit, or some general point in the future. So what do I need to do to make this more about this specific function? So, all right, so subtract 7. I'm going to write it in the front because I don't have room at the end. But yeah, negative 7 plus, or this minus 7. But I also need some numbers on here, and I probably have to fix up my variables a little because I want to represent f of x. So my starting dependent variable value, like the 6 feet in height from the previous question, plus what happens after that. So starting, if you want to imagine the same thing, we started underwater, plus what happens after that. What number goes down at the bottom here? 4.1. Now, I'm supposed to be creating a function of x, so I need to be 4.1 through x, which means that I need a different letter in here. But it's just a symbol representing, you know, something that goes between. So 7t plus 3 dt. T varies from 4.1 through x. You could use this, think about time. After time 4.1, we go forward as far as we want, but we started from a y value of, dependent variable value of, negative 7. So here's our expression for f of x, including that initial value in closed form. Or in open form. Now in closed form, sorry, second question. Think about the same sort of thing we did with the basketball velocity last time. If this is supposed to be the derivative of some function f of x, thinking about our closed form derivative rules, what must have been in that original f of x so that when I take a derivative of it, it has, for instance, a cosine in it? What would have been in the original f of x so that its derivative has cosine? Sine. So f of x involves a sine function. Sine of what, by the way? 7x plus 3. Right, when you take the derivatives of sine and cosine functions, that inner expression, whether it's an x or a whole other function, stays intact. So sine of 7x plus 3. All right, so let's see. Kind of going back and forth thinking and then checking and thinking and checking. If I take the derivative of this function f of x, I don't get quite what I want, but it's really close. I need it to come out 14 times cosine of 7x plus 3. If I take the derivative of just sine of 7x plus 3, what's the coefficient that we have in its derivative? 7. So what number do I need to put in front here to fix that? Yeah, if I put in a 2, you can see, if I take the derivative of this, f prime of x would be 2 times the derivative of this sine function, which is our cosine function, same input, with a times 7 from chain rule. And between this 2 and that 7, that gives us a 14. Now, is this exactly our function f of x? I don't really know. So this, we've got, just due to the accumulation that we know, we have this. But it's a little bit messier to figure out, well, what all is going on here. I have this f of 4.1 is negative 7. If I substitute in negative, does that come out? I don't really know. But think about this part here. This measures the accumulation between 4.1 and x. How could you write, if we know the accumulation is called f of x, how could you write this expression using just function notation and function f? What is this accumulation actually giving us? Well, this is the accumulation from 4.1 to x, or if this is a basketball, this is how much the height changes between time 4.1 and time x. If I had a function for the height, I just compare the two of them, subtract. So this integral would be f of x minus f of 4.1. And if you can see here, just to kind of point out, notice that this is f of 4.1. So you can see that just thinking about the meaning of the pieces, this should make sense. So if I have f of 4.1 and then add on an expression that tells me the difference between f of x and f of 4.1, then the sum of those two should be f of x. This is all called the fundamental theorem of calculus. But in any case, this expression here, we might be missing some stuff, but it's just a constant. We can find this, but I know that the rate of change of this, is going to be correct. All I need to do to finish this up is I've done all the calculus part. All I need to do is deal with some, well, arithmetic, essentially, trigonometry. But in any case, Wednesday, coming here ready for a quick 15 minutes, probably less than that, easy derivatives, and then we're going to continue talking about this stuff. I will see you on Wednesday, if not before. I've got office hours just now.